What's up, AP? Um, we are moving closer to the test. Remember that test is going to be on May the 7th at 8 a.m. And I'm pretty sure it's going to be on campus. Pretty sure. Now remember, if we miss this test, there is a retake on June the 2nd, and that will not be on campus, obviously, and we don't know the time. So I'm pretty sure the school has paid for this exam date. So let's make sure that we try to get there for that exam date. Now, let me erase. Actually, I'm not going to erase it. I'm going to leave that up there for us. So let's talk about chemical equilibrium. Chemical equilibrium. It's not a W, it's a U. So I want to do a brief intro to really express the why. Intro to equilibrium. So I want to express the why. And honestly, if you do a quick search on Google, you're not going to find there's a bunch of reasons to even discuss why chemical equilibrium is important in the real world. Because most articles on chemical equilibrium are going to be written to chemists, and they basically understand chemical equilibrium. But let me give you an intro to why chemical equilibrium is important to everyday life. So let's say that we go out and we buy some grapes. So grapes, let's make that purple. So we go out and we buy some grapes. I know there's green grapes too, but this is the traditional understanding of grapes. So we buy some grapes. And we want to take those grapes home and eat them and enjoy them, right? And so we buy them at the store and we take them to our house, right? Take them to our house. Boom, 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 boom. Okay, so now we get them inside and we have two choices. One, we can leave them on the counter with our cabinets underneath. We can leave them on the counter, put our grapes here. And what happens to those grapes over a period of time? Well, those grapes turn the color of the stem. They begin to, and I'm going to copy this and duplicate this just because I think it's going to be necessary. I don't want to necessarily do that drawing again. So if we take them home, put them on the counter, the recognition is that they will turn brown, right? They'll start to turn brown. They'll get these little moldy places on them. Eventually, they will not be edible. Well, they'll not be edible in the case that we like them. They will be raisins. But if we, at that point, do a little switcheroo, right? And we take them home and we put them in a refrigerator. Put them in a refrigerator. Let's go ahead and open the door here to this refrigerator. And we got drawers. And we got right there. We put the grapes inside of the refrigerator. Boom. Then those grapes are going to stay cool, right? And in other words, they are going to do what? They're going to last longer. And so what's happening here is that the general tendency of the grape and the chemical reaction that happens inside of these grapes is to basically decay, to go back and release its energy. The chemical reaction is to decay. But when we introduce them to the cooler temperature, we at least are able to, at that point, slow down this chemical reaction, slow down the reaction, and basically keep it in a cycle. Now, I know this breaks down, but we keep it in a cycle of what we call equilibrium. And it maintains its brilliant grapey taste. So scientists have figured out this process and how to make sure that the chemical reaction and the chemical reaction of making refrigeration happen will bring about equilibrium. So another one, let's talk about introduction to equilibrium again. So let's say we are wanting to, let's say we're going to travel. Let's do this. Say we're going to go from, I'm just going to draw a quick world here, put the United States in the center because that's what we do. We are arrogant enough to say that. So we have that. So say we're going to travel from this point and we're going to go down here, which is probably Australia. How are we going to do that? We're not going to swim this ocean right here. We're not going to do that. We're going to get into an aeroplane. We're going to get into an aeroplane. So let me see if I can draw an aeroplane. Boom, 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 boom. And that airplane, that does not look like an aeroplane, but it is. That airplane is going to go up into the sky, right? Now, what happens to the pressure as we go up? The pressure actually goes down, right? Pressure decreases as we go up. So what happens to our bloodstream as the pressure goes up is that it begins to lose oxygen. So oxygen, at that point, O2, is lost as we go up. Now, what happens in the airplane to make sure that it doesn't lose oxygen? Because if it loses oxygen, so much so, we're going to die. So what happens is that chemists have discovered that if they take inside of that airplane and pressurize it, that's just too close to that one. Take that and they pressurize it, right? If they put pressure on the inside of this airplane, then what happens is that the O2 levels are pretty good. Now, when that happens, a person can, here's my beautiful drawing of a person right here, boom, 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 that's a beard. A person may start feeling a little lightheaded when oxygen is lost, okay? So that is the process of chemical equilibrium. Basically, we take a little lightheadedness in order to stay alive because the pressure is Xing out this process of O2. And so chemists have figured out that when we fly, we need this process of chemical equilibrium in order to stay alive. Okay? So, and another example would be the concept of diving. You've got this diver who goes down into the water, right? Divers going down into the water, and they got, these fins on, right? And they got the tanks on their back, right? And they've got this mask. So they're going down into the water. What happens as we go down for pressure? The pressure actually increases. And what happens when the pressure increases? Then there is a release of nitrogen in our body. And too much of that is going into our blood, and as we come back up, that nitrogen is being released, replaced with a movement of oxygen. We have tricked our body into making more oxygen, and this person will die. And so what's happened here is chemical equilibrium is got this tank. It's releasing oxygen into our bloodstream. And then we understand through the process of equilibrium that we rise slow, right? We come to the surface slower in order to keep from dying. And chemists have discovered that the release of specific chemicals through that tank and the process of rising is a beautiful expression of equilibrium, and equilibrium is necessary for everyday life. It's also necessary for, say, for example, you have a field, right? You have a field, and in that field you have planted some corn, right? Some corn, right? And I know it's green, but we've planted some corn, right? And in order to get that corn to grow, then we're going to need some what? We're going to need some fertilizer. And so in order to create this fertilizer, then we need to use what is called the Haber process, which is N2 plus H plus, let's see, 3H2 is going to yield for us in equilibrium 2NH3. This is called the Haber process. It was also used in chemical warfare, but this Haber process is how we produce ammonia, and ammonia is good for fertilizer. And so chemists have discovered that if we keep this process in equilibrium, then we can actually eat food grown in a field. And so that's a simple introduction to chemical equilibrium and the why we need it. And so hopefully that helps. And when we come back, we're going to talk a little bit more about chemical equilibrium.